So we are going to start with history of progress of periodic table. So in 1789, Anthony Lavoisier published a list of 33 chemical elements, grouping them into gaseous, metals, nonmetals, and earths. So this was the fundamental start of this periodic table, or the journey of this modern days periodic table. That was started in 1789. In 1829, we came to about law of triads. So Dobeiner observed that when arranged by atomic weight, the second member of each triad was roughly the average of the first and third. Now let's see by example. So if you arrange by atomic weight, the second member will be roughly the average of first and third. So if you take this lithium, sodium, and potassium, so you can see the atomic number of 7 and here 39. So if you sum those two, you will get 46, and if you take the average, it will be 23. So lithium, sodium, and potassium in this triad, you can see the second member sodium that has atomic weight or atomic number average of this lithium and potassium. Similarly, in case of calcium, strontium, and barium, we can see that if you sum this calcium atomic number and barium's atomic number, if you divide it by 2, you will get roughly the atomic weight of the strontium. And these are some other examples. Not exact, but close number you will get. Next, German chemist Leopold Melin worked with this triad system, and by 1843 he had identified 10 triads, 3 groups of 4 and 1 group of 5. So this grouping was done based on the elements' nature, physical and chemical natures, because at the initial time they did not have any clue how to arrange these elements. So they started arranging them, they started grouping them based on their physical and chemical properties. For example, sodium, lithium, and potassium, they had common properties. That's why the scientists thought they can be in one particular group. Next, in 1850, this rule of integral multiple came. So Patenkoffer pointed out that the atomic weights of the chemically similar elements differ by an integral multiple of 8. So let's see the examples. For example, if you take this triad, lithium, sodium, and potassium, you can see the atomic weights are 7, 23, and 39. If you subtract 7 from this 23, you get 16. And if you subtract 23 from this 39, you will get 16. So that is the multiple of 8. Similarly, if you take this series, oxygen, sulfur, selenium, and tellurium, then you can see, if you see the atomic weights, these are also integral multiple of 8. So that's why he pointed out these atomic weight differences are integral multiple of 8. So that was also a key finding. Next, in 1862, law of Telluric screw came. So it states that the elements differing by 16 units in atomic weights among the successive members form a family of similar elements. So this has similarity with the rule of integral multiple. So in the integral multiple, it was said that the difference, atomic number difference, is the multiple of 8. And now here it is saying that the atomic weight difference is by unit of 16, which is also a multiple of 8. So Jancotis placed the elements in order of increasing atomic weights on the surface of a regular cylinder whose surface was divided into 16 equal vertical columns. Then a helix making 45-degree angle to the axis of the cylinder was drawn. The atomic weights were plotted vertically along the spiral line. In this arrangement, the chemically similar elements fall in a particular vertical column, and the successive members in the group differ by 16 units in atomic weight. The helical arrangement looks like a screw. That's why it is referred as the law of Telluric screw. Now I will show you the structure, how it looks. And if you see, this is the helical system, and they have made this 45-degree arrangement. If you see here, 16 equal vertical columns at 45-degree angle. So all these are the vertical columns. These ones are the vertical columns, and they have placed the elements one by one. So here you can see lithium, then beryllium, boron, carbon. So if you see the chart, so this wise, so from here to here, it is 16 columns. And when there is oxygen, in the backside also you will get oxygen here, and again you will get this one. So it's kind of a screw type of arrangement. And it was observed that the elements of similar nature, for example lithium and sodium, or if you take this boron and aluminum, carbon and silicon, they have the atomic number difference of 16. So that was a major observation. Next, in 1864 or 1866, in this range, this law of octaves came. So elements are arranged in order of increasing atomic weights. All 8 elements have similar properties. So Newland gives this law of octaves, and he said that all 8 elements have similar properties. So all those elements, whichever were known at that time, they have arranged according to the atomic weight. For example, if you see here, lithium, sodium, potassium. So if you go like this, if you arrange these atoms from top to bottom, and then next from here to here, so you will see these lines, these elements are similar in properties. So next, near 1868, Mendeleev and Lothar Meyer, so these two renowned scientists, Mendeleev and Lothar Meyer, so they independently noticed the properties of elements are periodic functions of their atomic weight. And then they independently tried to come up with their periodic table. But Mendeleev got most of the credit, and in 1871, Mendeleev published his short periodic table. So this one is the original Mendeleev's periodic table, and till that time only a few elements were known. All these 118 elements that we know now, it was not known at that time. So the discovery of noble gases came into the picture in the time of 1894 to 1898. Using two different methods to remove all known gases from air, Ramsay and Rayleigh were able to announce in 1894 that they had found a monoatomic, chemically inert gaseous element that constituted nearly 1% of the atmosphere. They named it argon. So Ramsay discovered argon in 1894 with Rayleigh, and after that he discovered krypton, neon, xenon in 1898 with Morris and Travers. And another noble gas element, radon, was discovered in 1898 by Frederick Ernst Dorn. Now in 1913, discovery of atomic number was done. So in 1913, Moseley discovered that atomic number instead of atomic weight is the fundamental property or the identity of an atom. So based on this, he proposed his periodic table. So basically, he had worked on characteristic X-ray and atomic numbers. So before this time, so scientists and the researchers, they were arranging the periodic table according to the increasing order of atomic weight. But atomic weight is not the sole identity or inner property of an element. Actually, the atomic number, that is the indistinguishable, or that is the main property of an atom. So that's why Moseley first said that atomic number uh, he discovered first, and that is the fundamental property of atom. Now, in 1922, the modern long form of periodic table came into the picture. That is also known as Bohr's table, because Bohr created his own version of this table in 1922, and based on experimental measurements of electron energies, along with some guidance from the periodic law. So Bohr's table added elements discovered since 1869. Now let's talk about Bohr's classification based on electronic configuration. If we see the inert gas elements, for these elements, the outermost S and P sublevels are fulfilled, having the electronic configuration Ns2 and P6. Thus, the zero group or group 18 elements are the members of this family. Helium is also included here because of the full-filled shell structure. These are generally chemically inert with respect to other elements. They generally remain as monoatomic species, among which the weak London dispersion force operates. So these inert gas elements, they do not tend to react. So if you mix different gas and if you put inert gas there, so these inert gas elements will not it will not react with the other gases or other elements. Now if you see the transition elements, these are characterized by the incompletely filled N-1 d sublevels. Evidently, for these elements, the two outermost shells are incompletely filled. Now next one is the representative or normal elements. So these are characterized by the incompletely filled outermost shell, that is the nth shell is partially filled, while all the other inner shells are completely filled. So these actually consist of the S and P block elements. So S and P block elements are called representative or normal elements. Now what are the inner transition elements? So these elements are having n-2f levels incompletely or partially filled, along with the partial filling of the n-1d level and nth shell. So thus, three outermost shells remain partially vacant in case of inner transition elements. Now let's talk about the Actinide Hypothesis. So for the discovery and investigation of 10 trans-uranium elements, Professor Seaborg has earned a share of the 1951 Nobel Prize in Chemistry. Now what is this? So at the early days, thorium, protactinium and uranium were mistakenly placed in group 4b, group 5b and group 6b respectively in D block. So in 1944, Seaborg pointed out this incorrect assignment and he proposed these elements to be the members of a new inner transition series analogues to the lanthanides. So this new inner transition series was described as actinides in his famous Actinide Hypothesis. So at that time, Seaborg was strongly criticized and warned not to publish his Actinide Hypothesis because it would destroy his scientific career. So see, this thing sometimes happens that if you want to publish something, if you are arguing something, so you will be criticized. The other people who are more knowledgeable or who know more in their field, they will think that you are making a mistake. The same thing happened with the Seaborg. So everyone warned him that don't say that there are something like called actinides or there are some different groups. Don't dare to publish these things. It will ruin your scientific career. So sometime later, after publishing that, so he narrated the event humorously as, I didn't have any scientific reputation, so I published it anyway. So this is the greatness of great scientists, that you believe in yourself, what you are doing, and ultimately, even in the long form of periodic table, you can see these actinides below these lanthanides. So he was right actually, but at that time, people criticized him. So he used to make a humor about that, and he used to say that I didn't have any scientific reputation, so I published it anyway. The actinide hypothesis saved the chemistry from a wrong direction. Seaborg and his group had synthesized many elements of the second inner transition series, that is actinides. Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.